Chemical and biochemical sedimentary rocks. So chemical sedimentary rocks, these involve the processes of evaporation and precipitation of minerals. We talked about forming minerals from solutions. Well, that's basically what's going on here. So minerals can be dissolved during weathering, and they are carried into lakes and oceans by streams and rivers. And then as the water evaporates, those minerals are left behind. And you end up with something like these salt flats over here. In hot, arid regions, high evaporation rates increase the concentration of dissolved minerals in bodies of water. The Great Salt Lake is one example of this. So you end up with highly salty water that's left, and then you'll have minerals precipitate out of that. And as the water evaporates, you also get these minerals left behind, these salts left behind in these salt flats. And again, this is more common in these hot, arid regions that have high evaporation rates and very low rainfall. So when the concentration of minerals in a body of water becomes saturated, crystals can precipitate out of the solution and settle to the bottom. That's kind of what's happening here. If enough water evaporates, the concentration of minerals becomes saturated, and then those minerals will start to form crystals and settle out, and you'll actually have a layer of these evaporite minerals. Gypsum and halite are two common ones, but these form on the bottom of these lakes. Evaporites are layers of chemical sedimentary rocks formed as water evaporates, and these tend to form in areas with minimal freshwater input and high evaporation rates. Arid regions, drainage basins on continents that have low water flow, and in coastal settings as well. So these tend to form in areas where, again, you have very little freshwater input, which would dilute the salt. If you have freshwater coming in, it would dilute the salts. You have high evaporation rates, so the water is evaporating fairly quickly. Arid regions are basically areas where you don't have a lot of rainfall. Drainage basins on continents basically are areas on a continent where you have water flowing into them, but there's nowhere for it to flow out. Biochemical sedimentary rocks. So these are formed from the remains of once living organisms. The most abundant is limestone, which is made of calcite. Calcium carbonate, which is calcium carbonate. The calcium carbonate dissolved in seawater is used to make shells. So the calcium carbonate is taken out of the water by a lot of organisms and used to make their shells. And then these shells sink to the bottom when organisms die, forming layers of carbonate sediment. And sometimes that gets broken down more, sometimes that gets left as shells, like in this coquina here. Coquina is just a type of limestone that has basically a lot of shell parts left in it. But during burial and lithification, more calcium carbonate precipitates out of the water, crystallizes between the grains of carbonate sediment, and that forms a limestone. So these are kind of glued together. These are bits of shell basically glued together by calcium carbonate that has precipitated out of the water. Then limestone in particular. Limestone is common in shallow water environments, such as off the coast of the Bahamas, where coral reefs live in 15 to 20 meters of water. A lot of that limestone there is actually the remains of corals, coral skeletons. Limestone can contain fossil evidence of their biological origins, such as shells here. Fossils can range from microscopic to very large shells that are visible without a microscope. Not all limestone is biochemical or contains fossils. Some limestone has a crystalline texture. Some consist of tiny spheres of carbonate sand called ooids. And then silica shells. So some organisms make their shells out of silica instead of calcium carbonate. And again, silica is SiO2. So basically they have glass shells or quartz shells. So this is microcrystalline quartz. Diatoms are one group of organisms that do this, and these are diatoms over here in the picture. When these organisms die and their shells sink, a sediment referred to as siliceous ooze is formed, and this is rich in silica, so there's a lot of silica in this. These are microscopic, so these are very tiny, so when they die, these shells are really tiny to start with. So you have all these little pieces of silica that are there. Then after lithification, siliceous ooze produces the sedimentary rock chert, which is very closely related to flint. So this is just a summary table of the different types of sedimentary rocks. So your main ones, you've got your clastic sedimentary rocks right here. You've got your biochemical sedimentary rocks, and you got your chemical sedimentary rocks. So the texture, grain size, clastic can be anywhere from very fine, which tend to be made from quartz and clay, things like shale, to fine, to medium, to coarse, which is basically up to your conglomerates and your breccia. You got your sandstones in here in the medium category, siltstone in the fine category. So again, those are all based on those particle sizes we talked about. Biochemical sedimentary rocks, you could have these are microcrystalline, so they are very tiny little crystals, things like chert is an example there. They'd have abundant fossils, so this is our fossiliferous limestone, shells and shell fragments loosely cemented together. You got something like coquina, microscopic shells and clay, basically chalk, which is this is also, all these are really kind of calcite right here, except for a bit of quartz right there. And then various sized fragments. So this could be coal, really. Coal is basically a type of biochemical rock. We said coal is not a mineral because it's organic, but it is a biochemical sedimentary rock formed from highly altered plant remains, and then some plant fossils are in the coal. And then chemical sedimentary rocks, you got the ooids, which are small spheres of calcium carbonate. Again, these are made of calcite, and this is oolitic limestone. Fine to coarsely crystalline, so this could be crystalline limestone. This is usually what we see if you get limestone to put on like a driveway or something. Fine to coarsely crystalline, again, you got dolomite. Very finely crystalline, you can have things like flint, chert, etc. These are silicates. Calcite, you get micrite. Fine to coarsely crystalline, again, you can have gypsum, you can have rock salt in here as well. So really, most of these are either, at least the biochemical and the chemical ones are either calcite or silicates, except for, really except for the gypsum and the halite down here.